So I'm just going to take a couple of minutes and walk you through the technique used to determine the formula that gives the angle of rotation of a conic. So we have the general form, but the issue here is we have this alarming looking BXY just kind of floating out there. We need to take care of that. All right, that can't be there. All right, if that's there, then we got a problem. All right, what we're going to do is we're going to assume we have a rotated conic that essentially needs to be straightened out. All right, that conic section is going to be in a particular form, and that form is going to be based off of this model. All right, except everywhere I have an X and a Y, I'm going to throw in a little prime. All right. So we also have to go back to some of the work that we've already done and use that information to make some substitutions. All right, and one of those developments came from the multiplication operation using the transformation matrix. All right, so that's what we're going to do is we're just going to kind of work off of that. You know, instead of reinventing the wheel completely, what I'll do is I'll just copy paste. So let me just go back and snag that information. I have it here. Right over here. Alright, so I'm going to go root and root. So paste that in. Now the result of this would be a transformation, specifically a rotation, right? And it would be in the form of x prime, y prime. All right, so carrying out that multiplication and associating everything properly, we get x prime equal to x cosine phi minus y sine of phi. Then we're going to have y prime is equal to x sine of phi plus y cosine of phi. Okay, so essentially we took the x, multiplied it by the cosine of phi, multiplied it by the sine of phi. We took the y, multiplied by the negative sine of phi, the cosine of phi, and then just added down the columns. All right. So that gives us a new relationship, which we can use to substitute. It ain't going to be pretty, but we'll get there. All right, so we can pop in this whole expression for, the x cosine phi minus y sine of phi for every instance of an x prime, and the x sine of phi plus y cosine of phi for every instance of a y prime. All right, so A, all that, plus B, well, I think I'm going to be shrinking, doing a little shrinky dink in here. So B plus C. My C looks like an open parenthesis, so let me make that look more C-like. CY squared, y prime squared that is, plus D plus E. And then finally, unfortunately, we can just tack on a plus F equals 0. So I'm just going to do some copy pasting here. Just bear with me for a sec. So we got that one. coefficient D corresponds with another x cosine, y sine. Alright, we're going to do the same thing, but this time with all of my y primes. This one I think we can just pop right in there. Yeah, okay, it kind of fits. And then one more. Well, that one's just huge. That need not be so huge. Get on in there. All right. So then the next step in the process is going to be the, apologies, it's going to be the fun part where we distribute all this stuff out. All right. So it's algebra. It's fun algebra. So let's just dive on in. I'm gonna reduce the size of a lot of this stuff here. Bring this up. Bring it in. And so we're looking at, some distributive property. And so you would expect some things to clean up somewhat. So we're going to have x squared cosine squared phi. All right. The outers would be x, y, cosine, sine, but there's going to be two of them. So minus 2xy cosine phi sine of phi plus y squared sine squared of phi. Now normally I would wait until we got some more information here before I started the simplification process, but I did want to point out, and at least talk about it, when you have your components here of x squared cosine squared phi and y squared sine squared phi, that's going to simplify nicely. All right. So those are the kind of things that we want to be on the lookout for. All right. So we just kind of keep that stuff in mind, because when we have the squared relationship, nicely is a strong term, but it's going to simplify. It's going to help us to simplify, because when we look at stuff like that, even though we can't combine them together, I see lots of cosines that are about to be multiplied by other cosines. There's going to be a way that we can make use of our Pythagorean identity, so we want to be on the lookout for that kind of stuff. All right, so the b is going to get multiplied by, this one's going to be a little spicier looking, but x squared cosine sine, so cosine phi sine phi, poor quality phi. Actually, who am I kidding? They're all poor quality phis. The outers would be x, y, cosine squared phi. All right, so that's what I'm talking about here. You see, now it's got a coefficient of b, but you see I have another term that's got a power of 2 for cosine in it. All right, so that's going to be helpful. All right, the inners minus xy sine squared phi. All right, another power of 2 associated with a trig function. Just going to keep that stuff in mind. And then a minus y squared sine phi cosine phi. All right, so that's the b term. The c term. All right, so you know what I'll do, because just for consistency, I'll make the plus go here. Then I'll throw the plus down here with a C. X squared sine squared phi. Outer xy, there's two of them. Sine phi cosine phi plus y squared cosine squared phi. Now the d, there's nothing really going on there. All right, so I got the d. Just going to keep that as is. Plus e. Plus f. And the whole thing's equal to 0. All right. Now, I mean, it's a mess, but there's a lot of stuff that can emerge from this. All right. Now, we can distribute through all of these terms. All right. So these coefficients, the A's, the B's, the C's, and then from there we can combine some like terms and see where that gets us. So now I'm going to carry out the distributive property. I'm going to do that on a fresh new page. All right, so let me take this work, bring it to the next page. Just smidge it down a little bit here. So if I run through with the A, now I'm going to get a little sneaky here. And maybe trying to get a little too sneaky. Let me see if I can get, I might have to erase some things. I think I might have lost a phi along the way. Oh, maybe I didn't. All right, so I'm going to distribute through the A, and let me just get rid of some of these highlights. Again, all that stuff I was talking about the powers, that's all going to be important stuff, so we're going to keep that stuff in mind. But I don't want to have to highlight it every single step of the way, at least not yet. All right, so I'm distributing through with an A. Then I'm distributing through with a B. Then a C. Then a D. Forgot the little I. An E. And in this, the copy paste, I lost my F along the way, so I'm going to just throw that back in there. All right, and these were all additions. All right. So it's still a sum, and it's still equal to 0. So now what I want to do is organize it so that all of my x squared terms are together. So I'm just gonna hand pick everything I need, anything that's got an x squared. All right, so that first term had an x squared. This one has an x squared. Throw in a little plus sign right here. It's really just the first three terms and the first three components. You can just do a copy paste right here. Alright. Because now I can GCF out the x squared and be left with the a, b, and c stuff, and that's all fine. Right? That result will be added on. And if we're thinking about the general form of a conic, the next term would be the xy term. So I'm going to grab anything that's got an xy. Let's see, xy, xy. Oh, there's two of them. There's two of them. Alright, it looks like we're down to this line here. A little out. Oh, I still got some room. Alright, then next up would be the y squares. Just going line by line here. Alright, then next up would be, let's see, it would be the x term, then the y term, then the constant. So whatever's just got an x attached to it, whatever's just got a y attached to it. I lost my dot. And then again, my lone constant at the end. Alright, and this is where I find out that I missed something, so let me just go back and double check. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15. So 15 components. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alright, so if I made a mistake, it wasn't in the number of items that are there. It's what I wrote rather than how many things I wrote. Okay, so still could be an issue, but hopefully not so much. All right, so I'm going to go line by line again. Always line by line with this guy. All right, so I'm going to factor out. I'm going to go a different color here, mix things up. I'm going to pull out an x squared, and that's going to give us a cosine squared phi plus b cosine phi sine phi plus c sine squared phi. Then in the next piece, I'm going to say plus, and we're going to yank out the xy. so plus xy. So we're going to have negative 2a cosine phi sine phi plus b cosine squared phi minus b sine squared phi plus 2c sine phi cosine phi. All right. Then the next one, we're going to pull out a y squared. So we're going to have a sine squared phi minus b sine phi cosine phi plus c cosine squared of phi. For the next one, I can pull out an x, which is just going to be d cosine phi plus e sine phi. Pull out a y. So negative sine phi plus negative d sine phi plus e cosine phi. And then we'd have the lone f at the end. Whole thing, again, equal to 0, as it's been. And now we're 2 pages in the books for this massive derivation. Okay, so now we're finally at the point where we can at least try to do something here. All right. The idea is that xy component needs to zero out. Now, if you notice any trig relationships that come into play, then make use of them. And that's what I was talking about before, where I'm saying that we might have some common factors. We might have some other attributes that would allow this this whole thing to kind of clean itself up. But whatever's going on here, this whole thing ought to become a 0. Now, it's not really the whole thing. It's more so whatever the coefficient. Oh, that was supposed to be a highlighter. Whatever the coefficient is of the xy, which really doesn't make anybody feel any better. But if we can figure out a way to make this part of it equal to 0, then we'll have everything we need. All right, so set it equal to 0 and solve for the value of, whatever, like you can just think about every other problem that you've ever done in a calculus class. And it's like, set it equal to 0, find a derivative, set it equal to 0. Just set it equal to 0, odds are that's the right way to go. Well, here again, that's the answer. The problem is it's easier said than done. All right, but what we can do is we can reorganize based off some trigonometric relationships. All right, so the first thing that I'm looking at are these two jammies here because they have a common sine phi cosine phi. So I'm going to rewrite as 2c sine phi cosine phi minus 2a, same deal, sine phi cosine phi. And then we'll have that other stuff going on, but you'll notice here, you can kind of skip a little step in the process. We have a common b, so it's going to be plus b times cosine squared phi minus sine squared phi. Let's move it on. And that whole thing is going to be equal to 0. All right, so I can factor out the sine phi, cosine phi. Oh, actually, I can pull out a 2. 2 sine phi cosine phi. And when I remove that as a GCF, I'll be left with just a C minus A. All right, plus B cosine squared minus sine squared. Yeah, that's not, unfortunately, it's not a Pythagorean identity, which we were hoping for before, but it's something, and that something would be the double angle identity, or a version of the double angle identity for cosine. So cosine 2 phi equal to 0. All right. Now, as it turns out, this is also a double angle identity. All right. This is sine of 2 phi. So we're looking at sine of 2 phi times C minus A plus B cosine 2 phi. Now, if we could only solve this for the value of phi, we would be able to determine, based off of coefficients, what the angle of rotation is for a rotated ellipse. Right? So, or depending on the conic, whatever the conic is. Okay, so what I'm going to do is I'm going to just move some things around. All right, so I'm going to vacate this term. All right, so I'll bring that to the other side. All right, so I'm going to have B cosine 2 phi, and that's going to be equal to a negative sine 2 phi C minus A. That's capital A. Jeez Louise. Like a rookie here. Then I'm going to take that negative and distribute it to each term here. All right, if you distribute it, it becomes negative C plus A, but that's the same as saying A plus C. A minus C. All right. So then what I can do is I can divide both sides of this equation I divide the left side. I want to get rid of that A minus C. So I can divide the left side by A minus C. It's going to cancel on the right side. And I want to bring the cosine of 2 phi over to where the sine of 2 phi is. So I'm going to divide that from both sides. It'll cancel here. And so we get this nice little ratio, which, sine over cosine is equal to tangent. Tangent of 2 phi would be equal to B over A minus C. All right. So if I want to figure out what the value is going to be for phi, I can take the inverse tangent of both sides. You do have to be adherent to the domain of the inverse trig function. But if I find the inverse tan of both sides, I get 2 phi equal to, like I said, inverse tan. Which allows me to solve for the angle of rotation by dividing both sides by 1/2, or, dividing both sides by 2, multiplying both sides by 1/2. So we'd be looking at phi is equal to 1/2 inverse tangent of B over A minus C. All right. And then the only thing you'd have to be mindful of is that there are domain restrictions for an inverse tangent function. All right, so when you go through the process and go with the attempt of solving one of these, you would want to make sure that you